Hi everyone, welcome to my talk on using simple learning models for detecting earthquakes in Groningen, the Netherlands. Before we go on and talk about simple learning models and why they are interesting, we must acknowledge that deep learning has created a sort of revolution in our society. And there are numerous success stories that have shown the power of deep learning, and we now consider deep learning as a potential tool to tackle long-standing research problem across the science and engineering disciplines. And the success of deep learning is mainly driven by its ability to find complex patterns without the need for feature extraction or feature engineering. And seismologists, like domain experts from other fields, have started to find value in deep learning. And if you were at the SCG annual meeting last month, you would notice that as a community, we have fallen in love with deep learning, and there are so many applications of deep learning that have emerged in seismology and geophysics in general during the past couple of years. However, deep learning comes with a few problems as well, and chief among them is the problem of interpretability of these black box models. Oftentimes, we go to these conferences and see remarkable results. However, we also find a lack of interpretation or lack of understanding of those results. Now, things are okay as long as we get good results, but it gets more worrisome when we find results that are not understandable or interpretable. For example, this is coming from one of the AI-based camera that was used to track the movement of a soccer ball in a soccer game, and the camera kept switching between the actual ball and the bald referee because it thought that this is perhaps the ball. And this, may make us laugh, but things can be fatal when a full self-driving car may crash because it falsely recognizes another vehicle to be something else, or an AI medical diagnosis system misclassifies patient's disease. And things like this have been happening around us already. Here are a few examples. And therefore, it makes us think more deeply about deep learning and what do the results mean. And we should try to understand what we get as an output from these deep learning methods. There was an interesting debate in the field of seismology a couple of years ago. It started with this paper being published in Nature that use deep learning to predict aftershocks. And the paper received a lot of media hype, and it was touted as a great success of modern science using deep learning. However, things got interesting when Arnold Mignon and Marco Broccardo showed that a logistic regression model with only two trainable parameters performed the same or better than the 13,451 parameter deep neural network of De Vries et al. Later on, Arnold Mignon wrote an article on why complexification of neural networks is not helping to predict earthquakes, and in general, it's not a good idea to approach any problem with. Similarly, Martin Ditkin, during his thesis at Oxford, studied a lot of different machine learning problems and compared the black box models with more interpretable models, simple models. And his finding was that on classification problems, these simple models perform the same or better than the black box models. And therefore, in this study, what we are going to do is we will try to see the problem of detecting induced seismic earthquakes in Groningen area using simple learning models, specifically the logistic regression model. And we'll briefly compare its performance with the CNN that we have also developed. However, for logistic regression model, we need to extract features, and therefore we use the HCTSA package, which allows automating this feature extraction problem, and it gives us about 7,700 time series features. Now, I should remind the audience that the reason why we are interested in simple models is because they are easy to maintain, debug, understand, and train, and therefore if there is a need of troubleshooting these models, it's much easier with simple models than with those deep neural network black box models. So as I was talking about the need for feature extraction, and as I mentioned that we're using this HCTSA package, which automates the selection of meaningful features by leveraging a large and interdisciplinary time series literature. And since time series are fundamental data objects that have been studied across scientific disciplines, methods to understand and extract useful information from these time series data have been developed over the years with a disciplinary context. So, for example, methods to study stock market data in finance have been developed largely independently of those developed for radiation dynamics in astrophysics, or those developed in seismology for studying waveforms, etc. However, HCTSA brings together a huge body of time series analysis literature by synthesizing these methods from across disciplines, resulting in a huge library of methods that can extract more than 7,700 features from a single time series. And what it gives us is something like a time series feature matrix, where on the y-axis you have, or the rows are each time series, and each column is a time series feature. So based on this time series feature matrix, and based on some labeling that you have for your data, you can do interesting stuff. For example, you can discover features that are more meaningful, that more meaningfully uh, distinguish between one class and the other, or you can study your data in reduced dimension, uh, for example, using this time series feature matrix. Let's switch gears and talk about the study area. So we're talking about the Groningen field, which is the largest gas field in Western Europe. It has been producing since the 1960s. Earthquakes in the region have been observed since the 1990s. And gradually, the magnitude and frequency of these earthquakes have increased. And therefore, uh, this led to a lot of problems in the area, which kind of forced the government to reduce production in the area first. And then this 3.4 magnitude earthquake in January 2018 led to a decision to close the field entirely. And therefore, this resulted in a huge financial loss for not only the operator, but the country itself. And therefore, this is an interesting um, case study for us to understand safer oil and gas operations in the future. So what we do is, because we were interested in this January 2018 event, we selected a window around that event. So we go to the KNMI catalog and select and find out events that have already been identified by KNMI, which is the Meteorological Institute in the Netherlands. And we find 47 events have already been identified in this period. These events range from a magnitude of zero point 0.2 to 3.4, with the majority of earthquakes between 0.5 to 1. We trim a 20-second window around each event, uh, and this forms our event class in our training data set, and we select noise windows from outside these identified windows. And later we kind of do some post-processing and stuff, which I'm not going into the details here. So once we have this data classes, what we do is we feed them to the HCTSA package, and we obtain 6,800 well-behaved features that do not yield something like an infinity or nan as output. And then to compare these features meaningfully, um, that may have different ranges, we normalize the output of this package. And we rank these features using a linear classifier and separating the two classes individually. So we get something like this. So we're looking at, for example, if you're looking at 50 top features, we can compare them pairwise using correlation, and we can then ignore highly correlated features. For example, from this block, we just need to select only one feature. For example, here, we can ignore all the features except one, and so on. So we end up with 4 well-discriminating features that we see on this slide. So the first feature here measures how time series properties change as points are removed from it. The second feature is a sliding window measure of stationarity. The third feature computes mutual information between two vectors formed by computing the mean and standard deviation of the time series in a sliding window. And finally, the fourth feature measures the level of surprise due to the next data point given recent memory. Effectively, all these features help us in distinguishing a signal that looks something like what we see in the middle panel, then the other panels in which we see noise manifesting itself in different forms. Then first we train and test our algorithm on these window data sets. So we get training accuracy of 99.3% and test accuracy of 99.3% as well. And then we wanted to test our trained logistic regression model with 5 trainable parameters, as I mentioned, for features, each weight associated to that, and a bias term. and we test it on a continuous record just to simulate how it would perform if you were to bring it to real-time earthquake detection. We use data of a 4-hour continuous window on November 1, 2016, starting at midnight. And the reason why we choose this window is that two events were already identified in this 4-hour window, and two relatively large events, 1.9 and 2.2 magnitude events. And therefore, we wanted to see if there were more events that were not detected by KNMI, and if there is something interesting going on in this period. So interestingly, these two events were estimated to be quite close to each other, and therefore, instead of running our algorithm on all the stations, we ran it on only 5 stations surrounding this the hypocenter of those two events. And to minimize false alarms, we require that we get a trigger at a minimum of 2 out of 5 stations from our algorithm. So we feed windows from all these 5 stations, and if at least 2 of those windows say that there is an event, then only we consider it as an event. Otherwise, we say it's noise. And here is the output of our uh, methodology. What we get, as you see here in bold, are the events here at 12:20 and 57:40 hours are the events that were already identified by KNMI, and both of them were identified by logistic regression model at all the 5 sensors. And we also see 5 other events that were identified with the timeline indicated here. While not all the events were identified at all the 5 stations, indicating that these were most likely low magnitude events, and they had much less signal to noise ratio compared to the other events. And another thing we did was to go back and look at the events that were identified by a single window. And in fact, we found many of those were false alarms or those were noise events, but we also missed some true events coming from that were only detected at a single station. So there's a price we have to pay in terms of getting this robustness, where all of these are actually true events, not even a single false alarm. Um, and this is the price we pay, that we miss a few small magnitude events. And therefore, there is room for improvement, definitely, in how we can make this algorithm more robust. Um, so we compare the performance of our logistic regression model with a deep convolutional neural network that was mainly done by my graduate student Ahmed, and he also presented this at the SG AI workshop. So I'm not going to go into the details of this algorithm, but I would just mention that by using this algorithm, we get the same events as well, because we feed in the same training data. So performance-wise, there is no difference between using this deep convolutional neural network and a logistic regression model that we use feeding in 4 well-discriminating features. Of course, the timing that you see here were slightly different in terms of seconds, because we were using a sliding window for deep convolutional neural network, but those are just minor details. It identifies the same events as we see here as well. All right, this brings me to the close of this presentation. So we explored the possibility of using a logistic regression model with feature extraction to detect induced earthquakes in Groningen. We use the HCTSA package for massive feature extraction from recorded seismogram. And I would like to remind here that the real value of simple learning models is not really in their accuracy, but it's in their ease of understanding, debugging, and training. And oftentimes we see that a lot of problems that we are using deep learning models from, and we are trading our understanding and transparency for these models, we get similar accuracy as we get with simple models, but we need to put some thought into putting together these simple learning models. The identified features, of course, also help us better understand the different classes present in the data. So if we can do this backward loop where we try to see, why are these features really meaningful for the classification problem we are solving, and this would help us even get an even better understanding of our data when things go wrong. Of course, a detailed study on diverse data set is needed to further validate the arguments presented here, and which we are carrying on right now. However, the proposed approach, I think, can be used to explore other problems in geophysics and seismology to address issues around opaqueness and overfitting associated with the black box models. And finally, I would like to bring this presentation to a close by mentioning that when automated decision making is done for a non-critical application, the need for transparency is somewhat tempered. So, for example, if you're trying to trying to, recommend a movie on Netflix, and if it goes wrong, I mean, it's not a big issue, right? However, in our field, in oil and gas and exploration and monitoring induced seismicity, I think it's highly critical, and therefore it's important to know where liability sits in case of failure, which is still a debated issue. So whether it's the company that was using this AI algorithm, or the company that built the algorithm, or the operators, or the technicians who were pressing the buttons, they are responsible, or is it down to us as researchers to build transparency into our models? And I would like to just mention here that AI systems that have a grounding in human logic rather than large data sets alone allow us to build models that are explainable, manageable, and stand up to the rigors of regulation. With that, I would like to finish my talk and thank you for your attention. And I would like to conclude with the message of this talk, which is that the training model should be as simple as possible, but not simpler than your data needs. And therefore, we should consider alternate algorithms rather than applying deep learning hammer to every problem at hand. Thank you for your attention.